Ora si registrerà la conferenza.
Geo-Storage technology. It's a real pleasure today to introduce you Romain Chassagne, which will have a talk and will introduce us to the dynamic reservoir characterization workflow for subsurface problems. This is a second seminar. It will basically tackle a second aspect, a second view within the Geo-Storage technology, and will introduce on a more modeling and mathematical side of this technology related to the manipulation of data within Geo-Storage. Just to get short, let me introduce a little bit. Romain Chassagne is essentially an applied mathematician by background, where he did his graduation in Bordeaux, University of Bordeaux, and his PhD there in applied mathematics. And then he traveled around, went to the Schlumberger Research Center in Cambridge, and then in IFP as a research assistant, getting introduced to the world of the applied, I would say, engineering and mathematics to the geosciences. And then he shifted in Heriot Watts University, where he's based as an assistant professor. And I would say he's an expert on applied mathematics and engineering modeling within for the seismic time lapses, history matching, and aspects that are related to groundwater as well, and CO2 sequestration and storage. Therefore, I think leave to Romain the word. Just a couple of words. You can follow this seminar as well on the YouTube channel, as it has been advertised on the various websites, Geotectonics and the website, so you can link directly from there if you cannot use the GoToMeetings. And in any case, the seminar will remain there for your perusal, so you can attend, access the seminar when you want, when you need it. Thank you very much for your attention. I'll leave the word to Romain Chassagne. Have a nice talk. Thank you, Romain.
Okay, hello everyone. Can you see my screen? Everything is all right? Hello?
Romain, we don't see your screen.
All right.
Romain, now you can. I have assigned the role of...
Okay, I need to share it again. All right, yeah, no problem at all.
You share again, yes, because probably before...
But you can still hear me, right?
Okay, it's perfect.
Okay, so you can hear me and see my screen.
Yes.
Okay, great. Fantastic. Perfect. So, hello, everyone. Thank you, David, for this very pleasant introduction. I'm not sure I'm an expert, but, well, I do some stuff, let's say. So I will present to you a dynamic reservoir characterization workflow for subsurface problems. I am Romain Chassagne from Heriot Watts University, and I'm very pleased. Thank you very much, David, for inviting me in this webinar, Geo-Storage webinar, and via the Italian Geological Society. So let's start. First, because in general, I'm rushing a bit to the end, I prefer to start with the acknowledgements here. So I want to acknowledge first some of my colleagues, close colleagues I'm working with on a daily basis almost. So first of all, Colin Macbeth, which I had a lot of discussion with him about this precise topic for a long time now, and we will probably still have a lot of discussion about that. Julian, Klaus, Hamed, Maya Daphne, who contributed to that as well, to compile, should I say, all the ideas. I also want to contribute to thank all the students, because actually this is the students who are doing the job of generating results, for instance. So I want to thank all of them for the two different projects. And finally, I want to thank my colleagues, because not so long ago, 1 year ago, we still could have some discussion around the coffee machine for lunch. And, you know, this is this kind of indirect feeding the brain which sometimes could end up on very interesting thinking. So we have an agenda for today. First, I will define the purpose and context. Then I will discuss some main issues. We will go on talking more on the data side. And I will also talk to you about a parallel way to look at the problem, subsurface problem. And finally, as usual, we will conclude and have some few remarks. All right, let's start with definition. Words matter a lot, especially with this kind of interdisciplinary domain where people are coming from different domains: geology, geophysics, reservoir engineering, computer science, sometimes math, rock physics, etc., etc. So you need to define clearly what you are talking about. So what I mean by reservoir characterization, so the word I'm using in the title, is sometimes used to refer to reservoir modeling activities up to the point when the simulation model is ready to simulate the flow of fluids. So mainly we have data, whatever data. We do a first reservoir characterization, and then we are able to have a simulation model, and then we can run it and generate some results. At that time, in general, it means that you are producing on your field, or you are exploiting at least your field. And because you are doing that, in general, you have monitoring data because you want to know more specifically what's happening down there and if everything is going according to the plan. So you need some monitoring data, and you have some. And then because you have this kind of on the fly new set of data, then you have what I call dynamic reservoir characterization. You could also call that history matching, data assimilation, data integration, or even inverse problem. That's fine. It's more or less the same thing, all of that. And you need this dynamic reservoir characterization or history matching in order to produce your field, to manage your field, to find some new infill drilling, to do some risk assessment, for instance, for CO2 injection and storage. You want to know if there is any leakage somewhere. You want to follow to see if the CO2 plume is migrating. This is applied as well to geothermal and obviously to oil and gas. I mean, mainly the method I will talk about in this talk has been developed in oil and gas framework, but it is absolutely applicable in geothermal and CO2 injection and storage. Okay. So now, just to be sure that everyone is on the same page and I'm not losing anyone on the way, I just want to introduce briefly, or to recap briefly, what is history matching process. So what do we have here? We have type of time series data. That could be pressure, bottom hole pressure, for instance, or production of something. And we have a kind of aerial coverage data, type of data. So map-based data. In that case, this is seismic data. And then you want to combine all these kind of data, but actually that could be, as I said, any kind of map-based data. That could be INSAR, ERT data, whatever. You have data mainly, and then you put that into your history matching box, and you hope that you will get a nice model update. Now, if we open that box of history matching, what do we have? So here, the orange box, this is your simulation model. You have some inputs. For instance, that could be porosity, permeability. You put that into simulation model, and then you obtained some results, like again, time series type of results or map, whatever, you obtain the results. Like again, for instance, pressure or production of something. And then you want to match that to observed, measured data on your field, on site. You compare the match in between the two, and if you think the match is too wide, then you are taking another set of input model, another set of porosity permeability, for instance, and you check again the misfit in between the data and the results from the simulation model. You are not happy, then you do that again, etc., etc. This is an iterative process, an optimization process, so it is done automatically. And at some point, you will find the lowest misfit you can get in between your data and your output from the model, which means that you find a nice set of models which represent enough the subsurface. I mean, you hope. Okay, that being said, now let's go back to our geophysical monitoring purpose or setting. Here, I just want to recall briefly what kind of geophysical monitoring could be used as data to do this dynamic reservoir characterization briefly. So here we have an example of the CO2 injection in Sala in Algeria, microseismic monitor. So microseismic is this red bits. So the microseismic events are characterizing the injection of CO2, for instance. Here at the Otway project in Australia, we have monitoring CO2 as well, CO2 plume while injecting. So this is here we have a time-lapse seismic data. Also for geothermal, so here it's a very interesting example. At that field, I won't pronounce it, I won't risk myself to pronounce this name because I did it with an Icelandic person and it was a disaster. So let's say this field, I hope you can see the mouse. So we collected seismic data, seismicity. And the thing is at some point, the production of the field, geothermal production, triggered a 4 magnitude event. And it has been felt at 20 kilometers from that field, and 20 kilometers correspond to Reykjavik. So they had a critical issue there, and they needed to investigate and to know exactly what's happening, if that would be just one event and that can calm down, etc. But for that, they would need a better model, a more representative model, because the model they had was maybe too rough. So what did they do? They did history matching, data assimilation with INSAR data. So they assimilate the data and then they get this answer of the model. And with this model, they could investigate it with more depth, the physics behind, so where the fractures, why the fractures have been triggered, etc., etc. I think it's probably, I mean, this paper is quite famous now in terms of 4D seismic use in oil and gas. So this one, 4D seismic helped to find a new infill drilling in place of another previous choices. And these new choices was a complete success, a breaking success. Here, another example of the use of 4D seismic at Sleipner. So a very nice example where 4D seismic has been used with great success to monitor the CO2 plume. So now with all these kind of different data in mind to characterize some aspects of what you want to monitor, what you want to be sure of, the main idea of history matching, again, this is to gather all these type of different data, so different scale, different physics, and multi-sources problem. You want to put that all together into this history matching box, and at the end, you hope that you will get a nice model update. And as you can guess, it is quite tricky because, again, it is a multi-scale, multi-physics, multi-sources problem. Very difficult. Still not solved yet. So usually we use this classical simplified workflow. Simplified because you can add a lot more detail than that. I just made it such a way that we just have the key component of this workflow. So mainly, briefly, you have seismic. I mean, you have data, any kind of data, any kind of map-based data. Again, that could be INSAR data, microgravity, ERT, etc., etc. And you have this area of the workflow, which is mainly the optimization. So you have some model at some point, you characterize your reservoir, you have a model, and then you want to discriminate among all these models, which one is the best representation of what you have in the subsurface. And you do that by matching to any kind of data you have. Now here in the orange boxes, I added some, which to me are main issues in this workflow. I cannot go through all of them. I don't have the time for that. But let's pick 3 ones. So the first one, model errors, for instance. This is something we probably, I mean, the community underestimated for some time, but now, maybe for the last 4 or 5 years, we are going back to that. And now we are doing some interesting mathematics to integrate these model errors into the big loop of uncertainty quantification, for instance. Another one I would like to talk about, this is the Petroletic Modeling. This one contained a lot of uncertainty and very difficult to trace and very difficult to quantify. How does it work? Well, so let's say in that example, you have seismic data, observed seismic, you have simulation model. In the optimization box, so the history matching by itself, you cannot compare directly pressure saturation to a seismic attribute, right? It's like comparing car and an apple. So you can't do that. You need to do some transformation. So you can transform seismic attribute into pressure saturation, or the other way around. You can go for pressure saturation to a seismic attribute. And then you can do your optimization because you are talking to the same scale of value. Usually in practice, what people do, and this is these papers I put here on the side, they stop halfway at the impedance level. Why is that? Because apparently it contains less uncertainty to stop there. Also, I don't think it has been proven in a quantitative way that it contains indeed the less uncertainty as compared to do the whole process. But also this is because very practically speaking, it's halfway for a geophysicist and halfway for a reservoir engineer. So then you are keeping everyone happy. Same amount of work, almost. And finally, the third box I would like to talk about concerning the issues. This is this metric comparison. So to compare your data, you need a metric to evaluate how close are your data, are the results from simulation model from the observed data. Usually within the community, we use least square sense, but well, least square is quite old and it's kind of rough metric, which is comparing one-to-one pixel comparison. If you think about it, that's a bit weird because especially for map-based type of data, you have patterns and shapes. So what you want at the end, this is comparing really, maybe even roughly speaking, patterns to patterns, geometry to geometry, the size of the shape to the size of the shape. One-to-one pixel comparison, we don't need that level of accuracy. So we tried some metrics from the computer graphics domain or computer vision domain, very sophisticated metrics, but actually the results were not so obvious in terms of improving the global history matching results. So I don't have any precise answer to that. Why? I don't know really. I just can guess that it's difficult to set up a fair history matching problem for two main reasons. The first one is it is difficult to get many data sets, and if you want to kind of give a conclusion on this kind of work, you need to try that on different fields, different real data sets. But as I said, it's difficult to get a lot. And the second thing is it's difficult to set up a history matching problem on a real data set. It takes a long time, and yeah, it's difficult. So for instance, in a company, roughly speaking, maybe I'm wrong, but I think it's around 1 year to set up a history matching on a real field case. So yeah, that makes this kind of study quite tricky to realize and to make some clear conclusions. And then the final bonus point I would like to make is that at the end of this history matching global workflow, there is something which is probably underestimated and something we don't do, especially in academia, which is results criticism. So at the end, when you end up by your set of models, the final ensemble of models, in general, we don't look into it really. we just trust the misfit. We saw that, oh, the misfit to the data are great. So the ensemble final of models should be fantastic. And actually recently, we tried a multi-objective function optimization algorithm, a fancy one, I would say. And it was very efficient to reduce the misfit. We obtained very good results as compared to other optimization algorithms. But when we looked into the final ensemble of models, it was not geologically speaking, it doesn't make any sense. So the optimizer forced the simulator, force the simulator to find some models which are reducing by a lot the misfit, but it is not giving physical results. And this is something I think I don't see too often in papers like this checking and result analysis, but it should. We should probably think about a way to do that. How, again, I don't know, I'm just kind of posing a question there. It's not totally obvious. If you can't just trust the misfit you get according to the data, well, I mean, manually speaking, yes, you can do it, but ideally you want to do that in an automatic way. So now let's pass on another side of the workflow. So I talked about mainly here the optimization. Now I would like to go back a bit on the data side. So I am aware that mainly I'm talking probably to the Italian Geological Society. So I took this example of Caesar and the Gallic Wars. So we know that Caesar in that text is quite biased, and he's helping to promote his political career and political ambition. So he's a bit twisting the facts and numbers, but we know that. So in general, we do facts check with other kind of data to know which one is true, which one is untrue. And actually data integration, data assimilation should be a bit that sense as well, because we cannot trust data 100%. It's not, I mean, we shouldn't do that. So in that paper, Dos Santos et al., they did a high, middle confidence and low confidence on the data, on the synthetic seismic data, but also observed seismic data, because of course you cannot trust both, unfortunately. So you have to really evaluate what you can trust from the data and what you cannot. And there are some works developed that way in the past. So there is this one, which is binary seismic history matching. So essentially you have your seismic data and you separate that into gas and water, gas in red and water in blue. And this is a for sure information, because we are doing a thresholding, so meaning that for sure what is red is gas and for sure what is blue is water. And then you update your simulation model with this information only. So again, only for sure information. And then you cannot mislead the optimizer towards a false direction to explore, a false bunch of solution to explore. You are just giving some reliable and trustable facts, information. Same idea here. For instance, you say, okay, these white patches are too noisy. Then please, optimizer, don't take these areas into account in the optimization, because then that will mislead you. So mainly you use a weight to put that on the objective function, or you penalize the objective function, and it works that way. Other authors explored other way, like characterizing the main event in your observed data and then match only that, because the main event you are almost sure of. So for instance, here you find the water flood front and then you match that. Or here they did reservoir connectivity, water flood, suitable sector, and channels and faults. So again, channels fault, for instance, this is for sure information I can see in the data. Then I will use that directly to update my simulation model, because maybe we don't need, again, going back to this idea of matching one-to-one pixels, we probably don't need to do that. So what I would suggest to do in this history matching workflow would be to add an extra step, which would be create a data prime before to go into history matching, which is a kind of cleaning, filtering, doing some confidence zoning within the data, or identifying nicely the main features within the data. Map-based or well data, I mean, time series kind of based data. That works for both. But doing this extra step, which for now, I'm not aware in any papers really doing that. We kind of do that before history matching, but it's very, very light. But I think this step is missing to really solve this history matching problem, which still is not really solved yet. So on an example, what do I mean by that? For instance, you have here a time series, here it's flat. You have a flat line. You probably don't want to give that to the optimizer because for him, he will interpret that as a physical meaning, but you don't want this, which is true, because if it is flat, it means that the device is broken maybe, or the device is in a cleaning mode or whatever. So there is a physical explanation behind, obviously, but this is not the kind of physics you want the optimizer to be influenced on. You don't want that, because then you will mislead the end results. So here we used a machine learning process to make it more physical, let's say. And here, same thing with well logs. We completed some missing informations or some noise informations with the help of machine learning methods. Same thing for map-based data, type of data. We could do that easily as well, identifying some main zone where we are sure of, where we can trust the data, and other zone where we cannot trust the data. So altogether, here I'm wrapping up this all this idea I talked about so far. So to me, there is an extra step to add before the history matching, which is working much more on the data and working from if possible, general way and in an automatic way. Like, as I said, identifying main features and use that to predict, or putting some patches where you trust the data and where you cannot. And then that will help to trace actually the uncertainty within the entire workflow. So again, as I said, the history matching problem is still not solved, and it exists for decades now. We still have problem in data integration, really, and I think this is probably one of the missing bit of this issue. So to me, history matching, the way we work on it in terms of research, it's a bit like this. So it's all of us, I mean, where we could fly in a plane, probably all of us have seen that once, someone trying to put a big bag in a place where obviously it doesn't fit, and like trying to force it, absolutely. So to me, history matching right now, it is at this stage, kind of. We are trying to push and to force all kind of different data in one same framework. Also, the framework is fantastic from a mathematical point of view. That's true. Very clever methods, very nice. But still, we are forcing some data we don't really understand, containing uncertainty we cannot really qualify into a big box. And then, yeah, maybe it's time to rethink a bit the strategy. I'm not saying that we should give up on this workflow. I'm not saying that. I'm just saying, as a researcher, we could try some other ways to do that. So this is what I tried, because I'm not always criticizing. Sometimes I try to give some potential solution. So let's forget about the equations here. So we tried this method with colleagues, which is you have here an example of injection of water. This is for the amplitude. You have injection of water, and you extract the water flood front in these two images. From there, you use this model here, simplified, and you try to predict the next front. So it's something much faster than the complex workflow. you have previously, and this is something doable on the fly. Like you have data, puff puff, you put that into the model, and then that's it. You have your answer in few seconds. So this is the results. I won't comment into details here because there is a paper there, and I don't have time. This is not the topic of this talk. But so of course this is just something starting. But the main idea is here, like, let's rethink the way we want to use the data. So we want to use data, we want to assimilate data for what? Well, we want to be able to predict the future in terms of production, in terms of plume movement. We want to assess risks, what if scenario, and we want to understand better the physics in the subsurface. So for now, we have many data like that, many parts, many bits of data, and we gather all together, all of them, and put in a box. What I'm saying is we should separate them, sync to them separately, and try to see if in a separate way we can use them in another way. And in this simplified way, you can probably better understand how you could use the data, where the uncertainty, what can you trust. For instance, this method that could work, that could be generalized and applicable on this example on Sleipner time-lapse image of the CO2 plume. So again, you have the water fluid frontier, and then you can use these two to try to predict the others. And same thing on this example, feed example in Denmark, which is a time-lapse electrical resistivity of a CO2 injection. So that is closing what I wanted to say about exploring parallel way to do some data assimilation. And while I was working on this project, I tried to find another paper trying to do data assimilation differently. I couldn't find anything. So yeah, apparently everyone is mainly focused on the data assimilation workflow per se, and yeah, that's the only example I could find. So now to summarize and to conclude, I really think to solve this data assimilation problem in a more accurate way and robust way, we should really rethink on the data itself. So going back to the data and evaluate what's within the data we have, again, whatever the data, INSAR, 4D seismic, etc., etc. And this is probably the only way to understand where is the uncertainty, how to qualify it, and maybe how to generalize it. And one other thing to do would be this data cleaning, confidence zone, extract main events, etc. Another point in generalization, as a former, very in another galaxy, former mathematician, I like generalization. So that would be very nice if we could generalize history matching, but we are really far from it because it's very field dependent. It's extremely difficult to generalize. I'm not saying it's not possible, but again, I'm coming back to this problem of you would need many real data sets to be able to have a good idea on what could work in a general manner on many fields. And this is difficult to access many data sets. And it is even maybe more difficult to set up a history matching on just one real data set. It's very long. So generalization, this is probably one of the things to finish with. Another point is automatization. So this is something everyone wants, especially industry, obviously. It has started already to some degree. There is example of Mazzoli et al. 2020, where they are identifying automatically faults with machine learning methods. And this automatization part, this is where really machine learning could play a significant role. And I think for that, they are really brilliant because that would be very useful to find which machine learning could be used in what of the boxes I showed previously in the workflow. making the entire workflow automatic, I don't think we are yet there, probably not. We still need the human brain to make some decision in between the box. But clearly automatization, this is about machine learning in that case, for the subsurface problem at least. And try other approaches. As I said, I would be very keen to see more papers on, yeah, okay, I tried this, which is different in order to predict directly or in order to assess, I don't know, a risk or assess something directly. And then from that, we could learn a lot on the uncertainty embedded within data. And finally, I want to acknowledge the Edinburgh Time-Lapse Project Consortium with all the sponsors who contributed to some of the ideas here in this talk and supported the students I talked about previously and myself. Also, references, so papers I cite in this presentation. And finally, if you have any questions, I would be happy to talk about.
Thank you very much, Romain, for your very interesting talk. It's touching one of the, we say, critical aspects of the, we say, data analysis and interpretation, what I call data conditioning. Very, very interesting. I would say that I open the question time. So anyone having a question or willing to do a question, please ask or get forward directly to Romain now, or eventually write it down on the chat, and I'll try to recontact you or read your questions. Any question then?
So in general, it means that you have been very clear, or the opposite.
Right, because I may start the question if you want, Romain, because I'm trying to extract what I could understand from your talk, which is I would say is pointing to very complex aspect of how we deal with the uncertainty, how we quantify the uncertainty, how we manage our, I would say, data result. And from my experience, I mean, especially when you deal with an aspect of the variables that you introduce, like the seismic interpretation, for example, when you're interpreting data across 3D or 4D, so data that in theory should be data that has been repeated in the same exact condition. And the real problem is to understand which is the main parameter which is affecting the uncertainty in our data analysis. So how do we design the conditioning, and if there are algorithms that help us to kind of design in a automatic, semi-automatic way our data set. But as you know, often each data set or each seismic data set has its own stories, processing story, is migration history. If you try to combine those data to cross-check the information of those data with well of data, those well of data got another type of data result and with different order magnitude of uncertainty. So it's, for me, the problem is which is the right way to do with that. And my impression is that there isn't a right way, but we have to force ourselves still to continue to do that. Otherwise, we risk to sell what I used to call smoke. We essentially we publish a result which we believe, or we force the people to believe, most from our prejudice on our approach, that is correct, till the next paper arrive and say, well, on the same data set I find something different. And most of the cases is exactly the problem of this kind of uncertainty on the data. So my question is, what is your experience as a mathematician coming across a community like the geoscience community, where we have a lot of parameters, most of the time very difficult to quantify? And how do you proceed?
So the direct answer would be it's a mess. Too many things are happening, and also this data assimilation problem, if you want to treat him in a practical way, which is the way industry would like us to tackle that. Well, it's difficult because it is an interdisciplinary problem. So, for instance, as you said, David, if you really want to quantify what's happening, the uncertainty, you need to have at hands the interpreter, the guy who processed the data, someone who knows about geomechanics, the reservoir engineer, the geophysicist, the geologist, and you need to gather everyone, and everyone needs to talk to everyone in order to understand where the uncertainty could come from and how to trace that. So that is one of my answers, to say that, yeah, it's complicated. It's really not easy. Something else you mentioned at the beginning of your question was a kind of sensitivity analysis. So, for instance, I'm not aware of any paper who tried to play with interpretation and see the impact on the history matching results, for instance. And the reason why is mainly what I just said, because it's a lot of different disciplines put all together, and then you have to find someone who will manage to follow the history of uncertainty. It's plus the mathematical frameworks you put on that to do some inversion, to do some automatic identification, to do some data conditioning, to do some cleaning, thresholding, level set method, maybe all of these things. So it's very, very difficult. So personally, I am torn in between two things. One which is okay, because it's complex, let's try to simplify the problem and let's try with a synthetic case. The problem is, quickly you will realize that in a synthetic case, you don't have enough reality. And then the conclusion you could make could be completely biased and completely divergent to the real case problem you would have if you would do that on a real data set.
Interesting.
So this is tricky. This is very tricky.
I got a question here from written, so I'm reading on the chat. Is, in your opinion, useful to fill the resolution gap between well-log data, millimeter 1 meter scale, and seismic data by using outcrop data to improve the geological model than to improve the overall model? So it's a more cross-scale problem.
Can you start the beginning of the question first? I didn't hear the first words.
Oh, sorry. I'm just reading. Is, in your opinion, useful to fill the resolution gap between the well-log data, seismic data, using outcrop data to improve the geological model, then improve the overall model? So,
so is it the? So again, the first words were what? Is it the European?
The resolution gap.
The resolution gap.
I think the question is more about asking, in the industry, we often use well-log data, which are millimeter to meter scale. We match resolution strongly independent which kind of seismic data you are using, in fact. If you are using the classical, I would say 0 to 150 hertz seismics, you have a resolution which is well beyond the well-log data.
Yeah.
So what about a classical way we approach to kind of smooth a little bit those aspects, to use outcrop data? The outcrop data are essentially data coming from geological data, which has a resolution which is something in between.
Yeah, well,
is that you are adding uncertainty from all three the case and scenarios. So how do you manipulate that?
Well, this is the issue. So you could do some calibration, which is well, that's yeah, that's not an easy question. So yeah, of course you have multi-scale data, as I said in the introduction, and you try to gather all of this type of data together. So how do you do that? Well, you have many different ways to do that. you could do I mean, I don't know, is it really so in a data assimilation perspective, you want to play with a simulation model. So you want to optimize what a simulation model will generate as a results, and then you compare that to your observed data, whatever scale. Okay, so in such a case, this is what you do. So for instance, you have well data, you can generate whatever kind of data from the simulation model, and then you want to feed that to whatever the scale of data you have. This is the way to do mainly. So yeah, you always want to add as many data as possible.
Yeah.
Whatever the scale, whatever the physics.
Yeah, thank you for the answer. Any other answer? Sorry, questions.
It's just a question. What do you think about the problem of uncertainty and versus scale? Because you know, as Davide said, we start from very different scale in the data set. I don't take into account the problem of survey acquired in different time with different processing different way, and this also a problem. But when you run a simulation in your reservoir, you are forced to work with very different scale data set, and so my point was to estimate the uncertainty with respect to the scale I am working. Is it wrong?
No, it's not wrong. Usually when you do this uncertainty analysis, or when you do this more complete data assimilation, you are comparing scale to scale. I mean, this is something you can do. So you really want to, whatever the scale, to compare all the data as possible. So this is a bit what I said as well when I was talking about you need to maybe rethink the data, because as you maybe mentioned, if I understood well, you want to preserve a kind of scaling factor in your data assimilation, and maybe sometimes you are not, because you are just kind of forcing data together. So one type of data could take over another type of data. Like for instance, in this objective function, you are using some weights, like you weight the well data, you weight the seismic data. And something I never understood is you do this equal weight, or sometimes people weight more the seismic or way more the well data, but based on what? It's not clear to me. And there are some other methods to avoid to do some weight on the data and then on scale, which would be through a multi-objective function, for instance. So you don't gather all the data in one piece of metric or objective function, but you separate that in different objectives to reach in terms of misfit calculations. And that would preserve maybe better the scale of the data you want to integrate. Because indeed, as you said, really, I think that your point is some scale data could take over some other scales in the optimization process, in the data assimilation process, which would be a problem then.
Yeah. Thank you.
Thank you.
Any other question? If there aren't other questions, there is a question I promised to myself I would have asked to every speaker, which is only marginally related to the talk. Well, it is somehow related, and from my point of view, I'm curious to see what is your view. I mean, the seminar we are proposing are a series of seminars in which we are showing how the technology, the science is progressing within the geostorage technology. Geostorage technology is part of a long, very, I would say, important societal evolution across our system, which is the way we are producing energy. So we are moving essentially from a fully controlled, I would say, fossil energy type of energy. We are moving into across the transitional evolution, which include the geostorage technology, to a renewable side. Now, my question to the previous speaker was exactly that one. I mean, we are moving from a system which was very profitable. It was producing a lot of money, and we are now usually investing into a direction which is the geostorage, which is much less profitable. In fact, it needs some subsidies to be sustained in a way or another. So, what do you think will be the pathway? What do you think will be the pathway in this direction? How long is it going to take this kind of process in order to be adopted by government and society? Because in order to be adopted in a way or another, we need to develop a technology which is at least self-consistent and able to self-sustain itself from a monetary point of view. What is your view on that?
So your question is on the economical and social side, right?
Yeah.
Okay. Well, that's a difficult one because I mainly do science and not so much of economics and society problems. But that's a good point, because actually we need to fund our research. So yeah, this is something I think everyone thought about. That's a tricky one. For sure, all the oil and gas companies are becoming energy companies in the future. That's quite obvious. Of course, the market in geothermal, for instance, is much smaller than oil and gas, obviously. Same thing for CO2 storage, probably, but I mean, the CO2 storage could be slightly different, because CO2 storage, it would probably depends on governments forcing a regulation, and then generating some obligation for companies to do that, to sell that product. But the rest, like geothermal, like low enthalpy, high enthalpy. So for instance, obviously we have some nice example like in Iceland and New Zealand and Japan as well to some extent. They are already producing since a long time some geothermal, and some companies, small companies, live on that perfectly well. So that happens in some part of the world, but unfortunately not everyone is sitting on some volcanoes. I think Italy as well, you have already some business in geothermal running for some years. Switzerland as well.
Yes.
So you see, so then the business model is working, but for smaller company. And to be honest, I don't know for the bigger company like the future oil and gas / energy company. I don't know how they will adapt to this new business model. I know little on that. I don't know. I really don't know. Probably they would need to shrink a bit, maybe, because they will have less money flowing. So probably they need to reduce the size, I suppose. And it will be a lot of diversification. Like it will be solar, wind turbine, maybe a bit of CO2 storage, because this is mainly oil and gas technology, geothermal, which is almost oil and gas technology as well. Yeah, probably smaller business, smaller companies at the end.
Interesting. Thank you very much. Looking if there is some of the colleagues that want to ask some question. If not, I think we can close here the discussion and presentation. And therefore, I have to thank you very much, Romain, for the nice talk and interesting point of view on the data. I would say data analysis and uncertainty analysis, which show us that there are a lot of complexity, mathematical and open question on this kind of side aspect. certainly this is a direction where we have to invest a lot of effort, because there is not a great tradition within geologists to critically discuss data.
So also on that, I would add that what I talked about is really like the concern and the current state of science in oil and gas. But for what I saw in some papers, geothermal, for instance, it's not yet there. For instance, I didn't see a lot of history matching papers regarding geothermal. So I think that there's some work to do in geothermal, like for data simulation. Like, I mean, in terms of same technology we use in oil and gas, applied to geothermal.
Well, a lot of things to be done. It's show that this topic, this subject, the Geo-Storage, has a very, very interesting and challenging scientific technological problem to be solved. Okay, I thank you very much for the talk. I invite you, all the audience, again for the next talk, which will be exactly in 1 week. So it will be on February, will be announced again across the whole various geotectonics and Italian Geological Society website, and we will be back again to a problem related to uncertainty, but from a more geological perspective and point of view. And it will be Juan Alcade from Barcelona institution. So see you next week. Have a nice weekend, and thank you very much, Romain, for your talk.
Thank you, David.
Have a nice evening.
Thank you. You too. Bye.
Ciao and bye to